Hello, welcome back to Chemistry in Action. In our earlier episodes, we came across many kinds of solids, liquids, and gases. In other words, the phases of matter. Today, we will take a longer look at these phases of matter. So, keep tuned to your program, and we will return after a short break. Look around us. Our environment has three physical components. One in the solid phase, the other as liquid, and the third as gas. The ground that people live on and build their homes is called the lithosphere. The lithosphere is a solid outer layer of Earth made up of a continuous layer of rocks about 100 kilometers thick. This river is part of what is called the hydrosphere. The hydrosphere also includes seas, oceans, lakes, streams, glaciers, groundwater, and all other natural bodies of water. The hydrosphere covers about 75% of the Earth's surface. The air around us and the gases that envelope the Earth make up the atmosphere. The atmosphere reaches up to about 500 kilometers above the Earth's surface, but 99% of the mass of the atmosphere is found in the first 30 kilometers or so above the surface of the Earth. These solid, liquid, and gaseous components of our environment serve as our life support systems. And studies show that life on Earth thrives best where these three phases of matter interface or meet in places like this. A plant like sugarcane absorbs water through its roots. The soil solution provides the plant the other nutrients it needs. During daytime, sugarcane absorbs carbon dioxide in the air and releases oxygen. The carbon dioxide is needed for photosynthesis. At nighttime, the plant absorbs oxygen from the air for its respiration and releases carbon dioxide. If water were not liquid, could it easily be absorbed by the plant roots from the soil and rise up the stem? If carbon dioxide and oxygen were not gases, could they pass through the stomata of the leaves? If soil were not solid, could it support trees and other plants? How we use things around us depends much on their being solid, liquid, or gas. What are the properties that distinguish each phase? In some restaurants, we sometimes find ice statues used as table centerpieces. Ice sculptors meticulously chisel the ice blocks to the shapes they want. A solid has rigid shape and volume. In the case of ice, it will maintain its rigid shape and volume as long as it stays frozen. But once it melts or turns liquid, it loses its shape. Its volume also changes because its density in its solid phase differs from its density in its liquid phase. Ice floats on water. This shows that ice is less dense than water. When it comes to this property, water is unique. It is the only substance which is less dense in its solid phase than in its liquid phase. All other substances have the opposite property. They are more dense as solids rather than as liquids for the same volume. This unique property of water is very important in supporting life and the environment. Protected from the cold by a layer of ice that floats rather than sinks in water, life thrives in lakes and oceans even during the winter. Solids are usually hard, but different solids vary in hardness. There are soft solids like lead and hard, heavy ones like iron. Some are brittle and crumble under mere pressure from our fingers. There are small, grainy solids like sand. Others are malleable like steel. Many of our farm implements and industrial equipment are made of steel. Liquids can easily be poured. They take the shape of whatever container they are in, but retain their volume before and after pouring. Liquids also flow just like rivers or streams. Being fluid or liquid, a soil solution is easily absorbed by plant roots and rises up the stem into the other parts of the plant. Our body cannot absorb and use the nutrients in our food unless these nutrients are in liquid solution. Some chemical reactions take place faster in the liquid state rather than in the solid state. The liquid and solid phases are called the condensed phases of matter. This is because matter in these phases occupies relatively smaller volumes than in the gaseous phase. We can easily observe and identify these condensed phases. A gas, like the air around the solid and liquid you see, cannot be observed as easily unless it is colored. But we can infer its presence in other ways. Arceli da Silva has here 2 empty dry bottles. She fills bottle A with tap water and bottle B with cracked ice. She then covers each bottle tightly and wipes the outside wall dry. Observe what happens. Droplets of water form on the outside wall of bottle B. We find no such droplets on bottle A. Where did all these water droplets come from? Could they have come from inside the bottle? Not at all, since the bottle is tightly covered. They could have come only from the outside. These droplets used to be part of the water vapor in the air outside the bottle, but they condensed or turned from gas to liquid due to the low temperature of the bottle. In the case of bottle A, the temperature of its wall is not low enough to condense any water vapor surrounding it. Vapor is any substance in its gas phase that exists either as a liquid or solid at room temperature, as in water vapor or alcohol vapor. We use the term gas for substances that exist as gases at room temperature, like oxygen or carbon dioxide gases. Water is colorless. That is why we cannot see it in its vapor phase. But some gases are colored, like bromine, chlorine, and nitrogen dioxide. Unlike solids and liquids, gases tend to diffuse or spread out even in a space already occupied by another gas, like the perfume that fills the air in a room. Because of this tendency to spread, gases have no definite shape or volume. When confined in a closed container, they will always fill up that container. We can fill a container with as much gas as the strength of the container will allow, and we call this property compressibility. We can fill tires or balloons with air, but there is a limit to the amount of air we can compress into a tire or balloon. Once we go over this limit, the tire or balloon will burst. That is, air inside suddenly expands. Then, accidents like this, due to blow-ups of tires, will happen. Substances in a gas phase, like the helium in this balloon, are always lighter than when in a solid or liquid phase. Gases have different densities. The balloon rises in air because the gas inside, usually helium, is less dense than air. After this uplifting discussion, let's pause for a short break. In our earlier experiment, the water changed phases from gas to liquid because of a change in temperature. Can substances change phases even when temperature does not change or is constant? To answer this, take a look at this tank of LPG, liquefied petroleum gas. It is stored as liquid in heavy-duty metal containers. The LPG is under pressure. It is forced or squeezed in to occupy a smaller space. Therefore, it exerts more force on the inside surface of the tank. What happens if we open the gate valve and suddenly release this force? The LPG liquid suddenly expands and vaporizes, turning into a gas that moves into the gas stove. This gas has no smell. To warn users of any leak, manufacturers add odorants, organic sulfur compounds that have a unique and powerful smell. When we smell them, we know that there is probably a gas leak. The experiments we saw earlier showed that temperature and pressure are the most important variables or factors that determine whether a substance will be in its solid, liquid, or gas phase. We can show this better with a phase diagram. A phase diagram shows the temperatures and pressures at which substances can exist at their solid, liquid, or gas phases. We can make a phase diagram by plotting points on it based on data from experiments. Let's make a phase diagram for water. Line AO is a melting point curve of water at different pressures. It shows that at different pressures, water melts at slightly different temperatures along line AO. Line BO is its vapor pressure curve at different temperatures. Vapor pressure is the pressure of the gas phase of a substance in equilibrium with its liquid phase. This means the liquid turns to gas as fast as the gas condenses back into liquid. It shows that water under different pressures will turn from liquid to gas at different temperatures. Line BO shows exactly at what temperature water turns to vapor for each value of pressure. Aside from melting or vaporizing, water also sublimes. That is, under certain conditions, solid ice turns into vapor. Sublimation pressure is the pressure of the gas phase of a substance in equilibrium with its solid phase. Again, this means the solid changes to gas as fast as the gas changes back to solid. Line CO is its sublimation pressure curve at different temperatures. It shows that with slight changes in pressure, the temperature at which water changes from solid to gas also changes along line CO. An area in the phase diagram represents a single phase, either only solid, liquid, or gas. A line in the diagram shows when two phases of a substance coexist at equilibrium. A point shows that the substance exists in all three phases at the same time. Gas, liquid, and solid are in equilibrium with each other. In this figure, the area bounded by AOB shows all the combinations of pressure and temperature under which only liquid water exists. The area bounded by AOC shows all combinations of pressure and temperature under which only solid water or ice exists. The area bounded by COB shows all combinations of pressure and temperature for which only water vapor exists. Any point on line AO describes a combination of temperature and pressure at which ice and liquid water coexist. Once the temperature or pressure changes, water, either a solid or liquid, disappears and becomes either only solid or only liquid. Along line CO, ice and water vapor coexist. Along line OB, both liquid water and water vapor are present. At point O, the temperature of water is 0.01 degrees Celsius and its pressure 4.58 torr. This is also called the triple point of water. Under these conditions, water can be found in the solid, liquid, and gaseous states all at the same time. Changing either pressure or temperature will make one or two phases of water disappear. Water sublimes or turns directly from solid to gas at pressures below 0.0098 degrees Celsius and at pressures below 4.58 torr. A reverse of this process takes place when frost forms in the freezer of a refrigerator. Frost is water vapor that has been directly changed into ice. In a refrigerator, a cyclic process of vaporization and condensation takes place. Vaporization takes away the heat from inside the refrigerator, cooling its contents. Condensation takes place in the compressor. Heat is released in the process. But the changes in the phases of water are much more important to us in a more basic way. In fact, without these changes, all of life on Earth would disappear. Life depends on the hydrologic cycle. Water moves around the hydrosphere, lithosphere, and atmosphere. As it does, it changes in phase, just as we described in the phase diagram. Powered by the sun, water from oceans, rivers, and lakes evaporates. It changes from its liquid to its gas phase. As water vapor climbs up the troposphere or lower atmosphere, it is cooled by the surrounding air as well as by expansion. As we go higher, the temperature falls. The boundary between the troposphere and the higher stratosphere has a minimum of -56 degrees Celsius. Before reaching this boundary, where temperatures are low enough, water vapor condenses into water droplets in rain clouds. This rain falls to Earth as rain or snow. This hydrologic cycle has been going on for billions of years. A molecule of the water we drink today may be one swallowed by Stone Age men thousands of years ago. We'll recycle this program back into your living rooms after a short break. In the past 30 minutes, we discussed how changes in phases of matter are essential to life. We looked into how solids, liquids, and gases differ from one another. Solids have rigid shape and volume. Except for water, substances in their solid phase are more dense than they are in their liquid and gas phases. Liquids flow. Liquids take the shape of their containers. Liquids retain their volume even when poured into other containers. Gases tend to diffuse or spread out in space. Gases have no definite shape or volume. We also showed you how to interpret and use a phase diagram. In the next episode, we will discuss the kinetic theory of matter. Until then, this is your host, Ramon Miranda, phasing out. See you next time.